Okay, can you see it?
Yeah, we can see the slides.
Okay, thank you. Okay, thank you, Professor Li, and thank you, Xinyin. And good morning, good afternoon, and good evening. Okay, my name is Han Su, and I'm honored to hold this section. And it's a pity that due to the the COVID-19 and we cannot gather together. But thank you for Professor Li to organize such a good, very good workshop, and we can gather together. Okay, and I think that maybe with the contribution of the talent expert and everyone's support, and maybe in this workshop we have organized AI challenge and on the AI security competitions, and we have gathered a lot of very effective algorithm, and I really appreciate every effort. I'd like to thank you all for the organizers, and thank for the sponsors in Alibaba, and also thank for Professor Li in UIUC. Okay, first, I think that nowadays AI security is very important, and maybe adversarial examples has attracted a lot of attention, and this is why we organize this workshop. And actually, in order to promote the development of AI security, actually, ever since the years in about 2 years ago, Alibaba and Tsinghua has organized these competitions, and we want to attract more students and more researchers to work on this direction. And ever since 2019, and it has attracted more than 40 subject people from more than 700 schools and enterprise around the world. And we have attracted many students to join the expedition road of AI security. Especially for this competition in CPR, we have more than 600 organizations, and I think that we have more than 3 subject teams, and as far as I know, this is the most. I think that we attract the most teams, and also we have more than 4,000 number of submissions. Okay, and we have also collect a lot of very effective adversarial examples and also very high quality algorithm. In this workshop, we have 2 tracks. The first track is about the white box adversarial attack on the machine learning models. And the first one is the purpose is to motivate the evaluations of adversarial attacks. Although we have known that a lot of adversarial defense models have been proposed to mitigate the threat of adversarial examples, however, some of them can be broken with more powerful or adaptive attacks, making it very difficult to judge and evaluate the effectiveness of the current defense and future defense. So without thorough and correct robustness evaluations, the progress of this field will be limited. So in order to accelerate the research on the reliable evaluations, we organize these competitions with the purpose to motivate novel attack algorithms to evaluate adversarial robotics more effectively. Okay, and all the evaluations is on open source platform, and this is about errors. Actually, it's developed by our teams, and nowadays it support more than I think that most of the mainstream adversarial attack and defense algorithm are supported. Okay, and also we have leaderboard online. This is the leaderboard, and even after these competitions, and everyone is encouraged to upload their algorithm to this leaderboard, and maybe you could for verify competitions about it. This is the final result for the track 1. I think that this is the top 10 teams, and most of them are from the top tier conference. And later, invited each team to introduce their algorithm briefly and effectively some key idea about their method and algorithm. Okay, the first team is team one and the green hand. Okay.
Hello. So, hello everyone. It is a great honor to share our solutions in the CVPR 2021 AI Security White Box Adversarial Attacks on Machine Learning Defense Models. My name is Ye Liu and come from the champion team Green Hand. Team's members include Ye Liu and Qilong Zhang, Lian Ligang. We are from the Chongqing University and the University of Electronic Science and Technology of China. My team's advisor is Professor Lian Ligang. For this competition, there are some restrictions. First, the average number of backward gradient calculation should be less than 100, and forward model prediction should be less than 200. In white box adversarial attacks, the number of backward propagation is very important. Since the restrictions, so we can turn this computation into a problem how to efficiently use the gradient calculations. In this computation, we have some findings. First, only part of examples that can be successfully attacked. Another part of examples is almost impossible to attack successfully. Among these can be successfully attacked examples, some of them are easy, but others are difficult. Secondly, we found that different initial points have a very important impact on the local maximum of loss. Some bad initial points converge to a poor local maximum of loss, and some good initial points converge to a larger loss. Thirdly, we found that fixed step size can't converge. In adversarial attacks, it is necessary to gradually reduce the step size. So, based on above observation, our motivation is to efficiently use gradient calculation and initialize to a good starting point. Our method is to filter out some that can't be successfully attacked.
Sorry. Hello. Yeah, sorry. Sorry. Hi. Hello, I'm here. Yeah. Sorry. Okay, I think that maybe there are some issues with Jie here. And then how about let's move on to the second group, and I will let Jie to continue his learning part. Okay. So maybe the top two is from it is Saint. Okay, the second group, I hear.
Okay. Hello, everyone. Can you hear me?
Okay. Okay. Thank you.
Yes. My name is Yuan Rui. I come from State Key Library of Internet of Things for Smart City, University of Macau. My partner's name is Gao Xitong, who comes from Shenzhen Institute of Advanced Technology, Chinese Academy of Science. Our team name is UMSIT. Now I'm going to introduce the main algorithms used in the competition. First, use the proposed new cycle laws in our recent work, Lafite, with the fast convergence speed and better attack performance. Then divide the model into robust and non-robust ones and design different strategy for each type. Optimize step size schedule using sample strategy. Adjust the number of iterations for different samples. First, I will further introduce the new loss function, which is the core of our algorithm. While studying the robust problem, we found that due to the exponential operation of the cross-entropy loss function, it is prone to underflow in floating point arithmetic. In some extreme case, the underflow will lead to the gradient-based attack totally failed. It means none of example can attack successfully. To solve this problem, we propose a new loss function by constraining the range of difference between the maximum value and the second largest value in the logits of the model. The figure on the right side shows how verifying the reciprocal constant temperature used in our new loss function from 0.1 to 280. The green line of the figure is the model's clean accuracy, and the blue one is the model's robustness attacked with the original cross-entropy loss. And the red line is our new loss function. On the right side, we can find the robustness of the model is equal to its clean accuracy. It means at this time, the gradient-based attack totally failed. And to our surprise, on the left side, the small error caused by floating point arithmetic also weakens the power of the attack. Based on the finding above, we constrain the temperature T equal to 1 during adverse attacks. Second, I will introduce how we design a mechanism that can automatically distinguish whether the model is robust or not. The main reason for this is that a proposed new loss function is very powerful and converges very quickly. So after the new loss function attack, we found the target attack could only slightly reduce the accuracy of the robust model, but could further reduce the accuracy of the non-robust model. Based on this finding, we designed a simple technique to distinguish if the model is robust or not. First, we use the 10 iteration attacks that use the untargeted target loss, followed by the top 3 targets of the DLR loss. We use DLR loss because we want to ensemble other methods to increase the performance. We classify model as non-robust if the model robustness dropped sharply during the target phase. We divide our remaining iteration by none to attack the non-robust model by the top non-targeted of our new loss function, and we will use our remaining iteration to attack a robust model by using the untargeted loss function. As the different attack settings are carried out in sequence, we allow new attack setting to continue working on the previous population generated by the previous attack. We further explore different choice of step size schedule, and we finally use the cosine as the final version. After each attack iteration, if the sample has been attacked successfully, we will stop further attack on the sample and allocate the remaining iteration to samples that have not been attacked successfully. To ensure that the attack strategy can generalize to new models, we search for the optimal configuration with relatively stable results and local hyperparameter changes. Our final result is 50.9607, and we won the second place award. Thank you for listening. That's all.
Okay, thank you. Okay, very good idea. Okay, then let's move on to the third group. Okay, S3L. Okay.
Okay. Hi, Professor Hang. Can you hear me? Hello.
Okay. Hello. Okay. You can start. Okay.
Yeah. Okay. Hello, everyone. I'm George, a PhD student from Shanghai Tech University. You can call me George for convenience. Our team name is our lab name. Thanks to the organizer of this wonderful workshop and competition, Alibaba Inc. Tsinghua University and UIUC. Just like the two teams said before, the main challenge of this competition is the overall query limitation. So if we use a standard PGD attack and allocate queries averagely on every input, it will lead to a lot of waste. Based on our observation in previous research, we found that for an adversarial trained model, about 15% of BNet samples can be attacked easily. About 14% inputs specify local robustness, which means that the attacker cannot find any adversarial examples for the inputs under the corresponding distance constraint. The left 10% of the inputs are the key point of this competition. These samples have adversarial examples, but need plenty of iterations to find them. So one optimization is to save attack codes on these easy and robust samples, and assign the queries to these 10% hard samples. For easy inputs, saving iteration is not a difficult task. We have plenty of ways to do this, just like early sort or add some random noise before backpropagation. But for robust inputs, detecting them is not an easy task in this competition. The traditional approach are based on software verification methods. For example, we can use interval analysis, abstract interpretation to check whether the input satisfies the local robustness boundary. Unfortunately, although the competition is a white box attack, we cannot obtain network architecture and weight. We can only use the gradient and network output. So we need an efficient approximation method to estimate robustness. How? We propose a novel attack method, outside inside attack, OIA. This is a workflow for our attack method. At first, we attack all of the inputs with an outside attack. This computation limits the max L inside distance. So outside means that we use a larger epsilon as a constraint. After the first round attack, if an input cannot find any adversarial example under this relatively loose constraint, then we think that this input cannot be attacked successfully in follow-up rounds. So we discard these inputs right away. Then, for these outside adversarial examples, we clip them into the original epsilon, if successful, which means that they are also adversarial examples and the original constraint. So we return them immediately. For the left field samples, we think these samples are 10% hard inputs, which have the potential to be successfully attacked and carry out follow-up attacks. Thanks to the author of EWR PGD attack, ODI PGD attack, and auto attack, we reference their algorithms and open source code during the competition. An interesting thing is during the outside attack, we optimize the two goals mentioned before at the same time. For the robust inputs, we distinguish and discard them with a few iterations. For the easy inputs, most of them could keep the stereo after inside clip, even if they transfer back to BNet after clipping. We also find a good start point for the follow-up attack. In the next slide, we showed the attack success rate on Metric Challenge CIFAR-10 model. With 100 queries limitation on each input, we can find that OIA can significantly increase the attack success rate. Corresponding paper is work in progress now. Finally, Professor Hang wants every team to share their future work. For our lab, we have done several works on several examples of attack, defense, testing, and verification. One thing I want to do in future is to use verification method to directly get the robust accuracy of a model. In this case, we can accurately obtain an optimal result on an adversarial trained model. But now the performance of this verification method is limited. That's all. Thank you. If any questions, feel free to contact me.
Okay, I have one quick question. Yeah, okay. Yeah, very interesting that you see that there's about 40% that is robust. Do you mean that these 40% examples, they are verified or cannot be attacked?
Yes, below is a formula to introduce the conception of local robustness. If we use some complete and sound verification methods, we can find these samples that which cannot be attacked successfully in this competition. But actually, we don't do verification, so we use an attack method to approximate it.
Okay. Okay, interesting idea. Thank you.
Okay,
next group. Okay.
Okay, I'm here. Yeah. Hi everyone, my name is Chuanbiao Song from Huazhong University of Science and Technology. Our team's name is Borderline. There are two members in our team, me and Jiadong Lin. So let me introduce our solution on the 12 white box attacks, which won the 4th place in this competition. For the gradient-based white box attacks, random sampling is important, since it can provide diverse initial perturb points for the attack success. Among the sampling strategy in white box attacks, currently the output diversified sampling ODS is the most powerful sampling strategy, which first selects a random direction in the output space, and then perform gradient-based optimization to generate the initial perturbation. However, for the ODS, the random direction in the output space may not be a good representation of the effective and real directions, which may limit the attack performance. Motivated by this, we propose a strategy named Random Real Target Sampling, RT, which aims to enhance the sampling diversity in the output space while maintaining the authenticity. Specifically, given a benign image as original, the RT first randomly selects a new image from the batch images as the target directions, and then use the cosine as the distance for the optimization. And finally, adopt the gradient-based optimization like PGD to generate the initial perturbation. After obtaining the initial perturbation, we will perform the regular PGD attack with the initial perturbation to generate the adversarial examples. As shown at Table 1, we report the major milestones for our adopted solutions. We can see that at the stage 1 of this competition, the sampling stage of the ODS can boost the attack success of the regular PGD attack. And our proposed RT strategy provides better performance than the ODS, which we can attribute to the diverse and real target directions. In summary, we propose a novel sampling strategy RT for the initial perturb points to boost the effectiveness of the white box attacks, and the RT achieves better attack performance than the popular ODS strategy. Thank you for your time.
Okay, thank you. And let's move on to the next group, okay? The cross-start PGD, okay?
Okay. Hi, everyone. We are very glad to know we have achieved the top level results in this competition. We are a small team from Indiana University Bloomington and the University of Wisconsin-Madison. We are here to share our solution called Fast Restart Projected Gradient Descent. Our solution focused on the efficiency of the attack, since the average number of backward gradient calculations and forward model predictions are restricted in this competition. Well, there are two phases in our solution, fast restart phase and the multi-step convergence phase. In the fast restart phase, an output diversified initialization version of margin decomposition attack is performed, compared with previous restart methods. Each restart of the fast restart PGD takes only a small number of backward gradient calculations. Therefore, the number of restarts can be guaranteed even in the case of resource constraints. Then several adversarial samples from the fast restart phase with the highest loss value are sent to the multi-step convergence phase. It is worth noting that although we choose the highest loss value each time, there is only a positive correlation between the loss value and the final success probability of the attack to a certain extent, but not absolutely. The more the number of backward gradient calculations in the restart phase, the stronger the correlation. However, this will lead to a reduction in the number of restarts or the steps of convergence, since the resources are limited. Therefore, it needs to be weighed according to the resources. After each restart, the computing resources are reallocated. Specifically, the resources of the samples that have been successfully attacked are allocated to the samples that have not been done, so that the unfinished samples can get a greater number of restarts. In the multi-step convergence phase, momentum iterative method is performed. We adopt scheduled step size instead of fixed one because we find that starting from large step size brings better results. Well, next page, please. Well, yeah. Here are our results. We can see that our solution has obvious advantages in the preliminary stage of the computation. And our method got a score of 50.8 in the final stage. That's all. Thank you for your attention.
Okay, thank you. Yeah, I hear. I think that maybe we should be back to the top one group. Okay. The green hand, yeah. I hear.
Hello?
Okay.
Oh, okay. Hello, everyone. It is a great honor to share our solutions in the 3PR AI security, white box adversarial attacks, machine learning defense models. My name is Ye Liu, and come from the champion team, Green Hand. Team's members include Ye Liu and Xirong Zhang, Lian Ligang. We are from the Chongqing University of Technology and the University of Electronic Science and Technology of China. My team's advisor is Professor Lian Ligang. For this computation, there are some instructions. First, the average number of backward gradient calculation should be less than 100, and for the model prediction should be less than 200. In white box adversarial attacks, the number of backward propagation is very important. Since these restrictions, so we can turn this computation into a problem. How to efficiently use the gradient calculations. In this computation, we have some findings. First, only part of samples that can be successfully attacked. A larger part of examples is almost impossible to attack successfully. Among these can be successfully attacked examples, some of them are easy, but others are difficult. Secondly, we found that different initial points have a very important impact on the local marxism of loss. Some bad initial points converge to a poor local marxism of loss, and some good initial points converge to a large loss. Thirdly, we found that a fixed step size can't converge in adversarial attacks. It is necessary to gradually reduce the step size. So,
Sorry, yeah. I cannot hear you. Let's repeat that. Yeah. Okay. Sorry, I think that maybe you have some problem with the internet, and I think that maybe they share some idea with the third group, and they found that there are some examples that can be easily detected, but others are hard, and they propose some clever ideas to maybe to find some initial point. Okay, I think that maybe it would be a very clever idea about it. Yeah, makes somehow makes sense. And congratulations for you. And actually, they have won the first place. Actually, this group they have some very good result in the AI challengers and in the that phase. And I want to mention that in the CIKM 2020, I think that this is about the object detections and also challenge, also organized by by Tsinghua and Alibaba, and they also won the champion. Very impressive. And maybe actually, yeah, we will release the maybe the technical report for this challenge. And nowadays, actually, we have finished the draft version and we will release it. I think that maybe after 3 PR. And at that time, I will ask you to include more detail about it. Okay, sorry about that. Yeah, maybe we have to move on to the next phase. Okay. Maybe we could include more technical details in the maybe in the technical report more. Okay, thank you. And actually, we have another track about the unrestricted adversarial attack on EP9. And this is actually, I want to mention that this topic is proposed by Professor Li and very interesting. And after discussion, all of the organizers think that this is the promising directions. And previously, actually, in track 1, we talked about maybe the small and small perturbations. But actually, in the accuracy, most threat to the deep neural network come from the unrestricted adversarial examples. That is, the attacker can make large and visible modifications on the image, but maybe from our human beings, maybe this is for some normal observations. I think that maybe previously there is some discussion about it. Such kind of the unrestricted adversarial examples can be referred to some maybe unmanifold adversarial attack, something very interesting. And so in this competition, we organize these competitions and select this topic. I think that maybe this is the first trial on these topics. Although previously there are some competitions, but maybe lack comprehensive evaluations. For these competitions, we ask a lot of human educators for the human evaluation. So we collect a large data set about for the unrestricted adversarial examples, and maybe later this year we are cleaning this data set and release the data set. We hope that this competition can will help the competition to understand and explore the scene on the unrestricted adversarial attack, but also we can further to understand the weakness of the current deep neural models and build a more robust image classification services. Okay, and this is for about the final result for the track 2, and we also have very good result on the maybe from different universities. Okay, and for this competition, students have proposed very clever idea about it. So let's move on about it. Okay, the first is adversarial random from the Peking University. Okay.
Hello, everyone. Can you hear me?
Okay, thank you.
Yeah. So, hello, everyone. Our team name is Adversarial Random. I'm Fangchen Liu from Peking University, under the supervision of Chao Zhang at Peking University and Hongyang Zhang, who will join the University of Waterloo as an assistant professor. In this competition, contestants had no information about the defense models, which belongs to the transfer-based black box attack. Unrestricted adversarial attack has received significant attention in recent years. However, generating transferable unrestricted adversarial examples is still difficult. It's important to keep high transfer success rate and good image quality, such that the crafted adversarial examples are not easily detected. In this competition, the adversarial examples will be manually scored from 2 aspects, namely consistent semantic and high perceptual quality. The evaluation metric, average total score, will only count the adversarial examples that are transferred to the tested model successfully. Besides, adversarial examples that have better image quality will get higher reward. Actually, there is a trade-off between the transfer success rate and image quality. Increasing the perturbation budget will improve the transfer success rate, but decrease the image quality at the same time. Given this trade-off, we aim to generate transferable adversarial perturbations with minimal norm for each image. Our intuition is that the minimal perturbation budgets with respect to distinct images are different, which depends on their geometrical distances to decision boundary over the test model. As we have no information about the test model G, existing transfer-based attacks that search for adversarial perturbations in a fixed radius number typically need high perturbation budget to reach a satisfactory transfer success rate. In our geometry-aware framework, we divide the attack in a number into multiple sub-procedures. In each sub-procedure, we start from the solution of the last procedure and rerun the attack algorithm. And most fixed radius attack can be integrated into our framework. The main challenge here is how to evaluate whether a given perturbation can transfer to the test model. We perform an early stopping. We leverage a validation model to select the optimal perturbation budget for each image. To get a minimum norm perturbation for each image, we perform an early stopping at the end of each sub-procedure if the probability of the true class on the validation model H is smaller than a threshold eta. The goal of the validation model is to prevent an attack algorithm overfitting to the training model F by forcing the final solution to cross the decision boundary of the validation model H with a certain margin. In fact, by tuning the threshold eta, we are able to control the trade-off between transfer success rate and the perturbation norms. Now let's go to the competition results. Please turn to the next page. In this competition, the image quality is manually scored by multiple human referees. We focus on L-infinity norm adversarial examples, and our training and validation model are both an ensemble of 8 high-performance networks. Our approach have a significantly higher average image quality. This improved trade-off between transfer success rate and image quality leads to a better final score. As the generated adversarial example shows, our method can assign adaptive perturbation budget to distinct images. To the best of our knowledge, we are the first to explore the method of using adaptive perturbation radius in transfer-based attack. We made further experiments in our recent work towards transferable adversarial perturbations with a minimal norm. In the even columns, we present the top 5 confidence bars of the test model for the images in the left. The ground truth label is marked by pink and other labels are marked by blue. In each row, the misclassified adversarial example with a minimum perturbation norm under a fixed radius baseline is highlighted by blue bounding box, which indicates that the perturbation budgets required for distinct images are different. Where our framework generates transferable adversarial perturbations with higher image quality, which benefits from the adaptive choice of our perturbation budget. And that's all my sharing. Thanks for your listening. Maybe is there any question?
Okay. Thank you, very clear there. Okay. Let's move on to the, okay, good at Warsaw. Okay.
Hi, everyone. My name is Chang Liu. I'm from Shanghai Jiaotong University. I'm a member of the team Good at Wing. Our team leader is Xiaoyang from Tsinghua University. We have got the 2nd place in the track 2 competition, and the competition set no limits to the modification range of the adversarial examples. We intended to solve the problem from a different perspective. Inspired by the noise-like perturbation-based pattern, we saw that the human eyes are not sensitive to high-frequency signal changes. So we introduced frequency analysis to the traditional gradient-based adversarial attacks. The benefit of a frequency domain is that different frequency bands can be treated differently to maintain the quality of the original images. The optimization problem can be formulated as the first question, in which F and F inverse represents the corresponding frequency domain transform. Our final decision is wavelet transform. the W represents the attention map to the decomposed wavelet coefficients. There are trainable parameters indicating the weights of different bases. The lowercase f represents the target classifier. Once the attention map is well trained, it can be used to generate adversarial examples from the second formula. The framework is shown in the figure below. In practice, in order to decrease the influence of color differences, which is perceptible to human eyes, we transform the original RGB color space to the HSV color space and set different multiplication ranges to these three channels. So the input image is first transformed to HSV color space, and then it is composed by wavelet transform. The coefficients element-wise multiplied by the attention map. Then the coefficients are composed to the original spatial domain image in RGB. The composed image is finally sent to the classifier to calculate the gradient to the attention map. From the signal processing perspective, the attention map can actually be regarded as a trainable filter. Let's come to the experiments. We have done some offline experiments on the proposed method, and some data augmentation strategies are added to the test. From the table, we can see that the proposed method has good attack success rate and the visual quality is the best, which is measured by two metrics, FID and LPIPS. And some of the adversarial examples are shown in the left down corner. Our method has less noise-like patterns, which means better visual quality from human eyes. During the competition, we have decreased the visual quality for sacrifice of attack success rate, which is more important in this competition. However, our focus on this competition is decoupling different frequency bands to improve the image quality of adversarial examples. Our team members are shown in the right down corner. Thanks for listening.
Okay, thank you. Let's move on to the third group, okay?
Hello, everyone. Can you hear me?
Yeah, okay.
Hello, everyone. It's a great honor to be here to show our work. I'm Wang Yajie from Beijing Institute of Technology. My team members are also from Beijing Institute of Technology and Guangzhou University. Their name is here. Our team called Demigods. Demigods is a very magical little culture in Harry Potter, which is powerful and invisible. It's a magical culture. So we use it as our team and our attacks name. As Professor Su just mentioned, the models are not robust. Some color changes, common corruptions, and perturbations, even spatial transformation can cause errors of models. The traditional adversarial attacks often use LP norms to restrict the perturbations to make the perturbations invisible to humans, but there is a problem with the LP norms, we think. The limitation of LP norm-based attack, firstly, the problem is these attacks are insufficient for assigning structured data in images because the attackers think the pixels are independent, which means the attackers can modify a single pixel in a large space, regardless the influence of other pixels, which means the semantic information of pixel loss, of the picture loss. And also it will change the spatial frequencies of images, make adversarial examples are easily spotted by humans. So LPIPS is definitely a good choice because the inspiration behind CNN comes from a concept called receptive field in the human visual systems. So we use LPIPS to restrict our perturbations. The pipeline of our work is very easy to follow. We use the output of perceptual networks as the perceptual loss between the adversarial examples and the clean image. And we optimize the perceptual loss and the adversarial loss together. For the optimization functions, we use MIM attack. And during the computation, we attack several models ensembles. The models are DenseNight, RepVGG, GhostNight, and nearly come out vision transformers. Next page, please. We would like to show some explanation of our research about unpredictable perturbations. Because of the progress of our perturbation generator relies on the perceptual similarity. Is to simulate the recognition of HVS. So the perturbation we generate is semantically informative. You can see after visualizing the noise, we can find it has something in the perturbations. In the examples, is 2 dogs. So we can say our approach is very successful. And in the adversarial examples, becomes only perform some luminance change which don't affect human vision at all. And we also feed the perturbations into the models for detection and found that the noise would be classified as a target class. So it's an offline experimental result here. Our perturbations will be classified as the target class at a very high probability, which is a very exciting result. And our related work is accepted by IGCAI 21. It will be available to you soon, and thank you for listening. Thank you.
Okay, thank you. Really impressive result. I think that I will read your paper. Okay, thank you. Okay. Okay, next group. Okay, Edward.
Hello everyone, can you hear me?
Yeah.
Oh, thank you. Hello everyone, our team is Edwards and the members come from Beihang University and CAST. They are Guo Qiuwang, Huan Qianyan, Ying Guo, and Chao Ning Zhang. We won the first place. Now let me introduce our solution. To improve the attack success rate, we should improve the transferability of adversarial images. Input diversity creates diverse input patterns, and the image will be transformed once randomly with a certain probability during each iteration in the processing of attacking an image. But this inspires us a question. The randomness brought by input diversity is always positive. If not, how can we counteract negative randomness? We design a method named gradient refining, which gets a refined gradient by comprehensively considering multiple gradients from multiple input diversity of an image. Let's see the framework of our solution in the right. The framework of gradient refining with translation invariant iterative attack algorithm is in the right. For an original image, we use input diversity several times to get multiple transformed images and calculate their respective gradients. Translation invariant method is used to apply the randomness. Then we return the positive information of gradients and counteract the negative gradients through average operation to get a refined gradient. Here, the negative gradient means a gradient that has a negative effect on improving transferability. We iterate the above process 40 times and get an adversarial image with high transferability. Except for gradient refining mentioned above, some useful methods are used in our solution. The model ensemble. We assembled the ResNet 50, DenseNet 161, Inception Net V4, adversarial trained Inception ResNet V2, adversarial trained in EfficientNet B5. We also use Gaussian smoothing, which used to flatter the high-frequency information of an image. We haven't used moment-based attack in our solution because the perturbations generated by moment-based attack show worse imperceptibility. Several original and adversarial images are shown in the left. Now let's see the next slide, please. Please, the next slide. Thank you.
Okay, I see it.
These are the results of our experiments. The correction time N plays a key role in improving the transferability. The transfer attack success rates continuously increase at first and tend to remain stable after the correction times exceed 11. Considering attack ability and computational complexity, the correction times are set to 11 in the following experiments. As the table shows, under single model attacks, the transfer attack success rates are improved by a large margin when using the proposed gradient refining on the listed attack methods. On average, the transfer attack success rates of gradient refining-based method outperform the baseline method by 6%. And we have higher transfer attack success rates under the assembled model setting. For more details, please read our paper that accepted as a poster in this workshop. That's all. Thank you very much.
Okay, thank you. Then let's move on to the next group. Okay.
Hello.
Okay.
Hello, everyone. It's a great honor to be invited to show our work on this international stage of CVPR. Our team name is Green Hand, and the members come from University of Electronic Science and Technology of China and Chongqing University of Technology. Here are the group members. They are Ye Liu, Yu Lei, Lian Ligao, and me, Xilong Zhang. Now, let's introduce our solution for the change. Our method is mainly based on the transferability of the adversarial examples. Before feeding the input into the substitute model, we first reduce the part of high-frequency component to boosting transferability. And then the size the image to 256 times 256, which can help save GPU memory. After feeding the input, we calculate the transferable direction backsetting method, such as MIFGSM, PIFGSM, DIFGSM, and so on. Since the gradient is calculated on an ensemble of model, it will be more close to the gradient of the black box model. However, conventional transfer-based methods are all based on same function to activate the gradient, which will ignore the difference among each unit in the gradient, thus leading to underfitting. Here is a graph. Besides, decision boundary of different GN are just similar but not the same. Therefore, overfitting like FGM is also less effective. To tackle this issue, we proposed a novel staircase method. Here we take staircase. Hello? Can you hear me?
Sorry, I think Hans internet dropped. Yeah, we are trying to find him.
Oh, okay.
Yeah, Han, please share your screen again. Hello, Han, are you there?
Hi, can you hear me?
Yeah,
Yes,
we can hear you.
Okay. Sorry about that. I lost the connection.
Okay. I'll speak again. Hello, everyone. It's a great honor to be invited to share our work on the international stage of CPL. Our team name is Green Hand, and the member comes from University of Electronic Science and Technology of China and the Chongqing University of Technology. Since the gradient is calculated on an ensemble of model, it will be more close to the gradient of black box model. However, conventional transfer-based methods are all based on same function to activate the gradient, as shown in the figure, which will ignore the difference among each unit in the gradient, thus leading to underfitting. Besides, decision boundary of different DNs are just similar but not the same. Therefore, overfitting like FGMS is also less effective. To tackle this issue, we propose a novel staircase method. Here we take staircase number k equal to 2, for example, as shown in the figure. Our method will assign different weight for each sign noise according to the original value in gradient. In this case, we choose 15 personnel as the threshold to assign weight. For example, if original value in gradient is less than threshold, we assign 0.5 as its weight. Otherwise, we assign 1.5 as its weight. As a result, our update direction will be more close to the black box model, thus improving transferability. We also conduct a simple population study before. For example, when the perturbation is constrained by L infinity norm 8, simply adopting PI-TI-DI FGSM only gets a score about 8. If we replace some method with our staircase method, then we can significantly increase score by about 14, which also demonstrates the effectiveness of our proposed method. Our paper is on the, please turn next page. Thanks. Our paper is now under review now, but we have made it public at arXiv. Here we show several experiment results for target tags. In each box, the left number is for SAM method and the right number is for our staircase method. As we can see, our method boosting target transferability by a large margin. More detail can be found in our paper. Any comments or suggestions are welcome. Thanks.
Okay, thanks for all the work in the in track 2. I think that actually I have one comment. Actually, all the ideas are very impressive, but actually I think that we have more in the unrestricted AdWords attack. I think that maybe in the last talk about from the CMU, the Dean's talk, maybe we can introduce some maybe external knowledge and for the tree structures VAE. That's a very clever idea. I think that maybe somewhat may be useful in the maybe in the unrestricted AdWords attack. Now actually maybe most of the current algorithm they are based on some of the pixel level AdWords attack. So actually when we design this topic, our purpose is at least one purpose is about how to design more semantic AdWords attack. I think that maybe everyone of you should think about it in the future. Okay, thank you. And maybe if you have do you have any questions about the previous work? Okay. Maybe you can, if you have, you may refer to the team names and maybe ask some questions if you have. Okay, if no, that'd be good. And maybe actually in October we will move on to the new chapter of AI security challenge in ACM/MM, and in this attractive and challenging event, we are going to explore the robust logo detections. And together with 3PR challenge and also the previous one, we hope that we could build an AI security ecosystem with academic and industrial forces. Okay, and thank you very much for your contributions and support on this section. And also, I'm looking forward to meet you next year, and stay safety and healthy. Now, I think that I may conclude this section. And hi, Professor Li and Xingyun. Okay, thank you.
Yeah, thanks a lot, Han, for organizing this session, and congratulations to all the winners of both challenges. So this is the end of all the events of our workshop. Then, like following this session, we will have poster sessions, and all the posters will be hosted in this Zoom room. So, if you click on the breakout rooms, you can see the titles of different papers, and feel free to go into the rooms to talk with the authors. Yeah, thanks a lot, everyone, for attending the event, and also the whole workshop event will be is recorded, and we will also release the recording online afterwards. Yeah, thanks a lot.
Okay. Bye.
Bye. Thank you.
Thank you.